Hi, this is Eric Bittner. I'm going to talk to you today about our work involving developing a novel kind of spectroscopy using entangled photons. This is work done by my postdoc, Hao Li, in collaboration with Carlos Silva at Georgia Tech and Andrei Piertinsky at Los Alamos National Laboratory. Thank you all for listening. I hope you all are safe and sound during the COVID-19 shutdown, and I hope to see you all sometime in the future. So in multidimensional spectroscopy, one of the difficulties you encounter is that it's difficult to distinguish between different orders of nonlinearity, especially if there are cascade processes involved, and this can lead to a confusion, and has led to a lot of confusion historically in understanding what exactly the signal that you're trying to measure. And one of the ideas that Carlos and I have discussed a lot in the last couple of years has been the idea that one can look at the two quantum energy and use quantum entanglement as a way to resolve some of the issues that you encounter in higher order spectroscopy, specifically because one can uniquely determine and discriminate between different Liouville space pathways if you invoke a quantum mechanical description of the photon field and measure things in coincidence and single photon correlation measurements in interferometry. So some of this is work very much inspired by work by Shaul, and as he has published on the last almost a decade, to some extent. Also Ted Goodson's work, which you mentioned, and most of that work is focused on the idea that one can, by tuning or turning the intensity of the laser down, where you're getting into the regime where you have single photons coming in one at a time or two at a time into the system. These photons are generally in an entangled state, and there's very strong time frequency correlation or anti-correlation in the time correlation function. And as a result, if you look at the two-photon absorption spectrum shown on one case over here, this is in rubidium, the 4s to 5d transition, as a function of the idler between the signal and idler mode. And what this means is that you've taken a two-photon state and broken it up into what's historically called a signal mode and an idler mode. It really doesn't matter what those are. And you look at this and you can get an enhancement of the signal. And likewise in porphyrins, and the work on the right is work by Ted Goodson. And what's interesting is that in the low intensity regime, the normalized two-photon absorption rate is essentially linear in the photon powers, and that's an important observation, because it means that in these very low intensity regimes, especially down here where I'm pointing with my mouse, you can in fact know that you are looking at a two-photon process as opposed to a single photon process, because the intensity is much higher, and from that one can use this as a gate. You can use other sorts of ideas for developing novel spectroscopies. Another kind of an alternative idea is that essentially what amounts to remote sensing. And this is what we refer to as the Kalashnikov-1 experiment, published a number of years ago, maybe 3 or 4 years ago, by a group led by Krivitsky. And in this case, if I could walk you through, you pump a nonlinear crystal and you split the signal and idler mode into a visible and IR photon, and you allow the IR photon only to interact with a sample cell, in this case containing carbon dioxide. And basically what you wind up doing is you pass it back through a nonlinear crystal, again doing you get a reflected and transmitted parts, and you look at the different signals that come out of this. The two-photon visible detection actually carries information about the single photon IR signal, and the reason for that is because these photons have become mixed and entangled by virtue of the action of this nonlinear crystal number 2. And so what this amounts to is one can do very interesting. This of course is linear spectroscopy, and of course carbon dioxide is, it's carbon dioxide. It's not necessarily a new and sexy molecule, but this allows you to do ideas, or think of ideas on how one can exploit quantum entanglement for doing other kinds of non-trivial spectroscopy. And I think what's interesting about this is that I'm not an experimentalist. I'm a theorist, but I definitely appreciate the difficulties in doing spectroscopy with IR photons as opposed to visible photons. The visible optics are much easier to deal with. And another experiment which we refer to as the Kalashnikov 2 experiment. The same group did a very interesting experiment, in this case placing the sample between a spontaneous down conversion crystal, one of the nonlinear crystals, and a beam splitter. It's basically the same experiment, and then did single photon counting experiments or coincidence experiments over here. And this particular setup is what's called a Hong-O-Mandel interferometer. And it's a very beautiful experiment. And essentially what happens in this beam splitter is the reflected component picks up a pi/2 phase shift, and you can look at the output photon field in the following form. This guy gets the reflected term gets an I, the transmitted term does not. And when you put all this together, you get a dip exactly at coincidence. And what that corresponds to is the destructive interference between this pathway and that pathway, as measured in coincidence, because the only way you can get a signal is if you simultaneously detect, or within a window, detect a photon here and a photon here. Now you could also do the experiment and detect 2 photons in one channel or 2 photons in that channel. However, there's an ambiguity, because you don't know, are these 2 photons actually coincident or not, or you might just get accidental coincidence. But in this particular case where you're looking at coincidence in different channels, you know specifically that those photons had to be entangled and so on. And again, we have this theme where the information about the sample is carried through to the entanglement between these 2 photons, and that's an important component of this nonlinear, of developing a nonlinear theory for quantum spectroscopy. And so from a molecular viewpoint, and from a molecular theorist point of view, it's this scattering term. That's what I refer to as the scattering matrix S here that characterizes the sample. So as a theoretical chemistry person, all of the molecular information that we want to put in must be encoded somehow into this scattering function, the 2-photon scattering function, or 3-photon or single photon scattering function, whatever you want. Depends upon the kind of spectroscopy that you're trying to do. Okay, so in this, going back to the Kalashnikov experiment, this is the Hong-O-Mandel interferometry without a sample, and this is simply a fit to the line shape of the SPDC crystal. It's simply an aperture function, nothing really interesting in this. If you put a time lag, and the time lag is introduced by simply shifting either the position of the beam splitter or shifting the position of one of the mirrors, and introduces a slight difference in the path length between one photon and another. In other words, you introduce a phase that you can interpret as a time lag between the 2 photons. And if you do that, you get one photon is delaying relative to the other, and of course interacting with the sample. It is another form of a time delay or time lag for that other photon. And again, you get an interferometry, which is a convolution of some sort of signal developed by interaction with the sample and the original line shape itself. And you can look at a YAG crystal, which is what this is, and you can look at nanocomplexes. It doesn't matter what you put in. And the inverse Fourier transform of this deconvoluted with the line shape gives you the natural line shape of whatever resonant media that you're interested in, very sensitively. And what's interesting about this is that you're looking at a femtosecond time scale process hundreds of, where you're getting resolution on orders of hundreds of femtoseconds. But the pumping laser is a CW laser. So it's a very cheap way to do femtosecond spectroscopy in a sense. Now, it's linear spectroscopy still, because we have not mixed two photon signals into the sample. But I think that's obviously the next stage in the evolution of this. So, which is what we're proposing. So, if you look at a molecular system, the way we look at this is, imagine that the molecular system is simply a network of excitonic sites that can move around in the site. Photon 1 excites maybe this guy, and it hops over here. Photon 2, well, I don't know, maybe photon 2 excited this guy, and he moves around. And so one of the photons excites one excitation, the other photon excites another excitation. They evolve and emit. So I have a transference in a sense, this excitonic network is acting like some sort of hyperpolarized, and it has a hyperpolarizability, if you want. It has two photons in, two photons out, fourth order type process that characterizes this particular system. And of course, now that this S2 is like the hyperpolarizability of the system, it includes or some sort of information about the dynamics and the many-body correlations that are going on within this hitherto undisclosed chemical system. It's just simply, for our purposes as theorists, it is simply just a network. It's simply a series of sites that we connect with a hopping integral. There's an interaction term. There are fermionic sites that in other words, there's an exclusion. We don't allow two excitons on the same site, so that the two excitons must move around in some sort of correlated way before emitting. And this one could include dissipative dynamics, relaxation dynamics. It depends how complicated of a theory you wish to develop, and how much patience and computation time you want to throw into this. But for a lot of the work we do, we like to do things more or less by pencil and paper, if we can, and then turn things over to a little more systematic ways of doing things. So we'll focus on the photon state, which is another key point here, is that in doing quantum spectroscopy, you have to include explicitly the full system isn't just a molecule plus a time-dependent radiation field that you treat semi-classically. You need to include the actual quantum states of the photon field and address the interactions of the material with the photon field itself, because for some very simple fact that even when there are no photons present in the system still is interacting with the photon field. So you need to properly dress the material part of the Hamiltonian with the photon field. So that's important to do. So all of the material terms we look at in a dressed representation that includes relaxation and reaction with the radiation field. But this is simply a scattering process, and you're taking an input state. There's a scattering matrix. You propagate an input state from minus infinity, minus time out to plus time, and take time to infinity, and that gives us the scattering matrix. Of course, this intermediate time is left unspecified because it doesn't matter when it is, because all the while the photon is interacting with material, and it's a different scattering boundary condition that you encounter in atomic scattering, because there is no asymptotic separation between the material system and the photon field. So you have to be a little bit careful in developing this. Okay, so how much information can we learn? So one of the key ingredients, one of the key things I think we have to think about is that, okay, great, there's all this big pile of money for doing quantum spectroscopy, but what do we actually learn? What new can we learn from doing all of this? Is there an actual payoff in terms of new knowledge, other than just simply saying, oh, hey, we're doing everything quantum mechanically, that's really cool? It's important to understand what new types of information we can get. Otherwise, why would you want to spend $millions and get the same information you can get from linear spectroscopy? There's no point in doing that. So here's what we think we can get. So the two panels really represent different dynamics. So even though they look alike, they're really different dynamics. A system is separable if I can uniquely write the wave function for one part of the system and as a product, or the wave function for the full system as a product state between this part and that part. That's an entangled state. If I can't do that, where I can't describe this dynamics without touching upon this dynamics, then the system is not separable and involved in an entangled state. The true description of the system is really a linear combination of the states of A and the states of B with coefficients C, A, B. That's a Fock state, and this is the kind of states that we deal with all the time in theoretical chemistry, but it's just a many-body state. It's a many-body entanglement state is a linear combination of different basis states of A and B, and there's an entanglement that evolves. We can write this in terms of photons in the same way. We can always write this entanglement in terms of what are called the Schmidt modes, and these are simply obtained by single-value decomposition of this CAB matrix to find a new basis, and those are what are called the Schmidt modes, and the Rn are the mode weights, and this is a basis, an orthogonal basis for the system. The phi's are orthogonal to each other, the psi's are orthogonal to each other, and of course it's the index between the two that's important. We can normalize this and calculate a von Neumann entropy, and this is a little bit of pedagogy, I realize, but basically if the system is uniquely separable, that only one term will contribute to this particular summation, and the entropy is 0, otherwise S is something that's greater than 0, because all the lambdas are less than 0, and so S is going to be greater than 0. And this entanglement entropy has some fundamental consequences, and it's a matter of, if I take the partial trace over 1 degree of freedom and divide the reduced density matrix of A or the reduced density matrix of B, the sum of the Schmidt coefficients for those two reduced density matrices are the same, which means they have the identical entropies, which means in terms of quantum information, entropy isn't an expensive property like we have in thermodynamics. It's a function of the contact between subsystem A and subsystem B. So all of the information we can learn about one subsystem is imprinted on the boundary between the two subsystems. And in cosmology, this is referred to as the holonomic effect, or quantum holonomic effect. It's basically used in describing black holes, because you can imagine the black hole is a subsystem of the universe for which we have no way of understanding what's going on inside of this, except for what happens to be on the boundary of the black hole itself. And so all the information we learn about the black hole, or about the material, if you want to think about the material as being the inside guts of the black hole, is imprinted on the boundary between the boundary between the material system and the photon system, and the probe that you're using to do this. So how do we actually calculate this? That's a little bit of philosophy, but let's think about how we would calculate this. So I want to write this scattering function in terms of a diagrammatic expansion, where I'm going to look at the squiggle line as being the intermolecular contacts, the intermolecular communications between pathway 1. Let's say this over here would be, for example, the scattering of photon with omega 1 to omega 1 prime for of just one photon. So whatever molecular interactions are going on, this would be the photon goes in, photon goes out, stuff happens in between, fully dressed by the radiation field and everything else. Likewise with omega 2, if you want to think about this in terms of a two molecular model, you would have photon number 1 encounters molecular system or exciton system number 1, does all of its stuff and leaves. Photon number 2 sees exciton system number 2, does all of its stuff and leaves, without any crosstalk or anything going on in between. But imagine that there's crosstalks. Maybe this interaction polarizes this interaction, and so I start seeing information exchanges between exciton part 1 and exciton part 2 of whatever sort this could be. They could be due to polarizations, they could be due to exciton exchanges, they could be all sorts of different kind of processes, which will simply leave to be unspecified because we want to develop a theoretical model. And so if there's no interaction, this particular scattering matrix is simply the product of the single photon scattering matrices. Nothing is going on. There's no entropy generated, no information regarding induced correlations within the system, and I can calculate that very easily. That's just the single photon response that I can write out in the following way. And omega I would be the intermediate, would be the photon energy, omega naught is the exciton energy, and gamma some sort of lifetime. And now let's imagine that each of these interactions leads to some sort of elastic scattering and maybe a phase, but it doesn't change the photons, or it doesn't change the frequency or the energy. It's just simply an elastic scattering, a randomization, if you want, of the phase of the scatterer. But they know about each other now through this dynamical either polarization or whatever kind of information that we want to put in terms of the specifics of this interaction. It doesn't matter what it is yet. Okay, and I can expand this easily. I can write out the nth order term and proceed and as you would, and renormalize and come up with Schmidt coefficients. So I can analytically, from this particular formalism, have a one-to-one mapping between the strength of the interaction, psi, and the von Neumann entropy, which I think is an important thing to point out, and that is that in a system that is generating two-photon entanglements, I have a one-to-one map now between the induced entanglement, the entropy, and the strength of the interaction. So given one, I can get the other uniquely without having to do any further calculations. I know what those are. We can do other kind of things. We can average over the phase. Well, what if the phase has some sort of uniform distribution? And again, I can come up with different models for the interaction, and different models for the scattering, and different models for the unseparability of the signal. Always written in terms of the strength of the interaction and maybe the noise of the signal. That's the noise, or maybe the fluctuations induced by the polarization of the other due to the other photon. And again, this can be separable. There's some squeezing. You get a squeeze state at the end of the day, and so on. And now let's dig a little bit deeper into understanding the nature of this interaction. So before we do, so again, you can write this in terms of the Schmidt decompositions, and this is nice little exercises in Mathematica if you want, and always come up with an entanglement entropy in terms of the interaction. So this is nice. So and so on. So what we have so far is a model that says, yes, if you have entanglement that's generated in the two-photon output state, you know that had to be due to some sort of internal interaction going on within the molecular system itself. And the nature of that interaction can be mapped directly onto the outgoing entanglement. So now let's imagine that the two chromophores rather, are linked in some sort of dynamical sense. And what I want to do is imagine that somehow that in this model I have some sort of stochastic interaction going on, where I have information being exchanged between one chromophore and the other chromophore, maybe via some sort of spectral density or some sort of bath that's mediating the exchange between chromophore 1 and chromophore 2. So what I can do then is develop an effective stochastic Hamiltonian for the pair of two-level systems that are now coupled to each other. And now let's ask ourselves, what is the two-photon response? So this is if I simply had one chromophore interacting with an uncorrelated media, this would be basically the development, what we would use to develop the Kubo theory. But now we have the case where we have two chromophores interacting with a common media, and both are possibly feeling fluctuations, the same set of fluctuations, or maybe not. And let's look at what would happen if we try to detect that with two photons. So the standard Kubo theory, each chromophore is independent of each other. We know how to do this. 1962, 60, whatever, Kubo told us how to do this. You imagine that the fluctuations are some sort of Gaussian noise, and I can write that interaction in terms of a strength and a time constant that describes the decay of the correlations, and I get a spectral line shape that depends upon the environmental fluctuations and so on and so forth. And this G term can be obtained very easily. This is the exact formula. And the different limits are, as we understand, if you have either a fast modulation or slow modulation, you have different limits of the Kubo theory. Now, if I include the cross correlations, the system is 2-point irreducible in the sense that I can no longer separate this into one Kubo response function multiplied by another Kubo response function. There's a cross correlation term, which we'll leave in this form. Now let's assume, because again I don't know what that is, but let's assume that this irreducible part also takes a Kubo-like form in terms of a cross correlation term. And again, I'll write it out as I would in Kubo theory. But the key is that I have to be very careful in the way I order these time, the limits in the time. There's only one of the times that I have freedom for. In Kubo theory, I can take both of these to 0, and then these guys are taken up to time t, so I have a single time. But in this case, I don't. I have to be very careful because I have to be careful when the different photons encounter the system. Although I can set 1 to 0. So I have 6 different time orderings as I sketch here at the bottom. The other 3 are simply just switch the colors, but don't switch the time orderings. And you can write out what the 6 integrals happen to be. And again, you have, much like Kubo, an inhomogeneous limit where the correlation time multiplied by the strength of the interaction is small, and you get a function, an entanglement function that only depends upon the intermediate time, which means that in this limit, this thing is fully separable. So which makes sense. If you have very weak interactions and very fast interaction, very fast decay of the time, the system is separable. However, if that's not the case, and you have the case where you have relative either strong interactions or long-lived correlations, the system is never separable, and the two-photon entropy now is a measure of the cross-correlation time between the excitation, because you see that right there is the term that survives in the inhomogeneous limit. So what this is telling you is that you now have an unambiguous way to measure whether or not chromophore 1 and chromophore 2 are talking to each other via the environment. Okay? And we can write this out and analyze this in more detail. There is an optimal time or optimal strength for the entropy. This is mapping the entropy onto the strength of the interaction, the cross-correlation magnitude, and you can also pull out what the individual time correlation functions are, or rather the Schmidt modes of the time correlation function for the system, if you wish. Now, I'll put this in a little bit more specifics. Let's write this out in terms of an H versus or H and J aggregate type system, which is a system we like to study because it's a little more of a molecular system than simply saying, well, things are just interacting in a polarizable media. So let's look at the following. Again, this is something we can work out relatively straightforwardly. We have two chromophores, two uncoupled qubits that talk to each other via some sort of single exciton exchange mechanism, but they also talk to each other in the excited state, that in the sense that there's an energy cost to put the system in the doubly excited state. Okay, so I can again write this out in terms of a Hubbard type model. The interaction strength U is the anharmonicity to put the second photon into the system, or second excitation into the system. There's a photon bath and exchange interaction between the excitons and the photons. And I can again write this out for two-photon scattering in terms of Feynman diagrams. Again, this is a fairly straightforward calculation to do. You can work this out analytically from this point, and it's in our recent JCP paper, if you want to see that. So if we look at the two-photon scattering amplitude, again, looking at this as an entanglement, as a way to generate entanglements, omega 1 and omega 2 are the two input states, and from that I look at the entanglement of the output state. Again, I can map out uniquely by looking at the entropy that's generated. I know, first of all, I can discriminate between H and J aggregates, which really isn't a big deal because we know that it's an H or J aggregate, for a system by looking at the just the emission from a single chromophore or from the chromophore dimer. But we also can pull out of this again a mapping between the entropy and the exciton-exciton interaction term, which might be a little more difficult to get in normal spectroscopy. So in this case, we have a mapping. If you want to think about it, if you can tune the J coupling, which you can do in some conjugated polymer systems, you can basically switch the system back and forth between one kind of a J aggregate versus an H aggregate, and so maybe in this case we could have a tunable source for generating entanglements by looking at either the pressure or however you're going to tune the system between H and J aggregates. And Frank Spano is here. We'd appreciate this picture of the Dr. Jekyll versus Mr. Hyde. TIPS tetracycline or polythiophene has this really nice double-sided sort of system where it can be either J aggregate or an H aggregate depending upon the conditions in which it was produced. And so maybe hexathiophene is a useful system for probing for this. But we can also look at the two-photon scattering probabilities, which if I plot things in this way, it looks a little bit more like your traditional nonlinear spectroscopy signal, and that's exactly what I want to try to point out with this, is that in the two-photon, this is now looking at one photon goes in and one photon and the complement going out. Now these things are linked by the fact that energy is a conserved quantity. So if I look at omega 1 in and omega 1 out, of course the system has to be symmetric. I could look at omega 2 and omega 2 prime. It doesn't matter. If I look at, so if I set omega 2 to be resonant with this intermediate state, what we can point out is a few things right away. Notice that in this case, this would be the H aggregate case. I can see both omega B, which is the exciton case, which is the dark exciton, which you would not see in an emission spectrum. But you can also see the coupling between the splitting between the single exciton state and the two exciton state, so omega CB. So in other words, C, if I go back to my level scheme, back here, is this guy right here. So I'm pulling out this energy difference and this energy difference. So I'm pulling out the two-photon state and the single photon state in all of these cases. Now, if I have the case where the intermediate state is exactly in the middle, which can happen in a number of situations, either with U equals 0 and J equals 0, or as I sketch back over here, well, I guess there is a case where if I'm right along this line in terms of the interaction strength and the exchange coupling, then I'm always in a separable case, and I will not see this the splitting. Here's the omega B. I see the splitting over here, but I don't. It's sort of fairly boring spectroscopy in a sense. Much more interesting spectroscopy in probably the more realistic cases where I have either an H aggregate or a J aggregate, which I'm pulling out now all of the cross correlation terms between the different levels within the system. And of course, we have more levels and more complicated, and go and see far more complicated signatures if you wish. But in this very simple 4-level system, already we see some very rich many-body dynamics coming out of the model, at least. And this is simply plotting in a slightly different way, omega 1, omega 2. Now you can see this is looking at the full output state, and you can see again this is how it's symmetric in omega 1 and omega 2 prime in terms of the output state. But you can also see how I can pull out complementary information. I find it more interesting, or maybe a little more informative, to look at the correlation between the input and the output of the pump and the probe versus the two probe signals. But that's nobody has done this experiment yet, so who's to say which is going to have the more utility in terms of understanding what's going on in the molecular system. So I believe this is a powerful way to extract exciton-exciton correlations in a chromophore network, maybe the light harvesting 2 complex. Now these are related to what are called two-photon cascades, but we pre-select the input as a two-photon input, two-photon Fock state going in. We show how all of this is limited by cross correlations between excitons, and these are the relevant papers that we've written in the last number of years discussing this, and we have a number of other works coming out with Carlos looking at two-photon tomography of the singlet-triplet fission process and other dynamics going on in two-dimensional perovskite systems, which I'll talk about hopefully if we ever get to another ACS meeting at some time in the future. I can present that information. So again, I want to acknowledge Dr. Hao Li, my postdoc at U of H, Carlos, for many years, going all the way back to our work on cell-weighted electrons in 1995, when Carlos was a graduate student and I was a postdoc. Andrei Pirutinsky, who I've collaborated with for many years again, a great friend at Los Alamos at National Laboratory. Ajay is Carlos's former postdoc, who is now soon, hopefully, if all of this quarantine stuff blows over, we'll be starting a position at Wake Forest. And some of the work we did with John Jerke, looking at how to do the decomposition and two-photon decomposition in a very efficient computational way. So with that, I'll end, and I hope you all are sitting safe, and thank you all for watching my presentation. Bye. I just have to figure out how to end.